Suppose I take my space is examples now. Space is say the column space of this matrix. Let me write down a matrix. 1, 1, 1, 2, 1, 2, and just to make it clear, I'll take the sum there, 3, 2, 3, and let me take the sum of all, well, let me put in 1, yeah, I'll put in 1, 1, 1 again. Okay. So that's 4 vectors. Okay, do they span the column space of that matrix? Let me repeat. Do they span the column space of that matrix? Yes. By definition, that's what the column space, where it comes from. Are they a basis for the column space? Are they independent? No, they're not independent. There's something in that null space. Maybe we can, so let's look at the null space of the matrix. Tell me a vector that's in the null space of that matrix. So I'm looking for some vector that combines those columns and produces the 0 column. Or in other words, I'm looking for solutions to Ax equals 0. So tell me a vector in the null space. Maybe, well, this column was that one plus that one, so maybe if I have one of those and minus one of those, that would be a vector in the null space. So, you've already told me now, are those vectors independent? The answer is, those column vectors, the answer is no, right? They're not independent because, you knew they weren't independent. Anyway, minus one of this, plus one of this, 0 of that is the 0 vector. Okay. Okay, so they're not independent. They span, but they're not independent. Tell me a basis for that column space. What's a basis for the column space? These are all the questions that the homework asks, the quizzes ask, the final exam will ask. Find a basis for the column space of this matrix. Okay. Now there's many answers, but give me the most natural answer. Columns 1 and 2. Columns 1 and 2. That's the natural answer. Those are the pivot columns. Because, I mean, we begin systematically. We look at the first column. It's okay. We can put that in the basis. We look at the second column. It's okay. We can put that in the basis. The third column we can't put in the basis. The fourth column we can't, again. So the rank of the matrix is, what's the rank of our matrix? 2. 2. And now that rank is also, we now have another word. We have a great theorem here. The rank of A, that rank R, is the number of pivot columns, and it's also, well, so now please use my new word. It's the number 2, of course. 2 is the rank of my matrix. It's the number of pivot columns. Those pivot columns form a basis, of course. So what's 2? It's the dimension. The rank of A, the number of pivot columns, is the dimension of the column space. Of course, you say. It had to be. Right. But just look for one moment at the language, the way the English words get involved here. I take the rank of a matrix. The rank of a matrix, it's a number of columns, and it's the dimension of, not the dimension of the matrix, that's what I want to say. It's the dimension of a space, a subspace, the column space. Do you see? I don't take the dimension of A. That's not what I want. I'm looking for the dimension of the column space of A. If you use those words right, it shows you've got the idea right. Similarly here, I don't talk about the rank of a subspace. It's a matrix that has a rank. I talk about the rank of a matrix. And the beauty is that these definitions just merge so that the rank of a matrix is the dimension of its column space, and in this example it's 2. And then the further question is, what's a basis? And the first 2 columns are a basis. Tell me another basis. Another basis for the column space. You see, I just keep hammering away. I apologize. But I have to be sure you have the idea of basis. Tell me another basis for the column space. Well, you could take columns 1 and 3. That would be a basis for the column space. Or columns 2 and 3 would be a basis. Or columns 2 and 4. Or tell me another basis that's not made out of those columns at all. So, well, I guess I'm giving you infinitely many possibilities, so I can't expect a unanimous answer here. I'll tell you, let's look at another basis, though. Because it's only 1 out of zillions, I'm going to put it down and I'm going to erase it. Another basis for the column space would be, let's see, I'll put in some things that are not there. Say, oh, well, just to make my life easy, 2, 2, 2. That's in the column space. And that was sort of obvious. Let me take the sum of those, say 6, 4, 6. Or the sum of all of columns, 7, 5, 7. Why not? That's in the column space. Those are independent. And I've got the number right. I've got 2. Actually, this is a key point. If you know the dimension of the space you're working with, and we know that this column, we know that the dimension DIM, the dimension of the column space is 2. If you know the dimension, then and we have a couple of vectors that are independent, they'll automatically be a basis. If we've got the number of vectors right, 2 vectors in this case, then if they're independent, they can't help but span the space. Because if they didn't span the space, there'd be a third guy to help span the space, but it couldn't be independent. So it just has to be independent if we've got the numbers right. And they span. Okay. Very good. So you got the dimension of a space. So this was another basis that I just invented. Okay. Now I get to ask you about the null space. What's the dimension of the null space? So we got a great fact there. The dimension of the column space is the rank. Now I want to ask you about the null space. That's the other part of the lecture, and it'll go on to the next lecture. Okay. So we know the dimension of the column space is 2, the rank. What about the null space? This is a vector in the null space. Are there other vectors in the null space? Yes or no? Yes. So this isn't a basis because it doesn't span, right? There's more in the null space than we've got so far. I need another vector at least. So tell me another vector in the null space. Well, the natural choice, the choice you naturally think of is, I'm going on to the 4th column. I'm letting that free variable be a 1 and that free variable be a 0. And I'm asking, is that 4th column a combination of my pivot columns? Yes, it is. And that will do. So what I've written there are actually the 2 special solutions, right? I took the 2 free variables, free and free. I gave them the values 1, 0 or 0, 1. I figured out the rest. So, do you see, let me just say it in words. This vector, these vectors in the null space are telling me, they're telling me the combinations of the columns that give 0. They're telling me in what way the columns are dependent. That's what the null space is doing. Have I got enough now? And what's the null space now? We have to think about the null space. These are two vectors in the null space. They're independent. Are they a basis for the null space? What's the dimension of the null space? You see, those questions just keep coming up all the time. Are they a basis for the null space? You can tell me the answer even though we haven't written out a proof of that. Can you? Yes or no? Do these two special solutions form a basis for the null space? In other words, does the null space consist of all combinations of those two guys? Yes or no? Yes. Yes. The null space is two-dimensional. The null space, the dimension of the null space is the number of free variables. So the dimension of the null space is the number of free variables and at the last second give me the formula. This is then the key formula that we know. How many free variables are there in terms of R, the rank, M, the number of rows, N, the number of columns? What do we get? We have N columns. R of them are pivot columns. So N minus R is the number of free columns, free variables, and now it's the dimension of the null space. Okay, that's great. That's the key spaces, their bases, and their dimensions. Thanks.